This is Physical Science 2, Chapter 12, Part 2 on Earth's internal processes. In this portion of the video lecture, we will be discussing earthquakes. The Earth is a fairly restless place. We learned in our last video lecture that the lithospheric plates are constantly moving around. Some are running into each other, some are pulling apart from each other, and some are grinding side by side from each other. When we talk about earthquakes and global earthquake distribution, there is an earthquake on this planet roughly every 30 seconds. Now, we don't get late-breaking news stories every 30 seconds about a new earthquake on Earth because of several reasons. One, if you think about the water versus land surface on the planet, there is more water. There are a lot of earthquakes that are underwater that we cannot directly feel. They are measured by scientific equipment and seismographs, but we cannot feel them. Also, for the fact that earthquakes do have to be strong enough for people to notice them and to cause damage. And for the most part, not to say that you can't have a random earthquake in the middle of a plate, but earthquakes usually occur in very well-defined zones. And those zones are along the edges of the lithospheric plates. And again, not to say that we can't have some within a plate, but generally they occur along those plate boundaries. So why do earthquakes happen? Seismic vibrations are caused by the rapid release of energy from all of this plate movement. And in general, earthquakes are associated with transform boundaries. So when the ground shakes and quakes, we can get some damage that occurs. When we talk about deformation of materials, strain on any material will occur as a response to stress. And stress is how much force you're putting on that material per unit of area. And basically, all materials on the planet, whether they are man-made or natural, they can only take so much stress before they will undergo strain and deform. There's a couple of different types of deformation that can happen to materials. A compression force is a squeezing together of forces. Compression forces are often associated with a convergent boundary. Tension forces, these occur when forces pull apart, much like at a rift valley or the mid-ocean ridge, a divergent boundary. A shear force occurs when forces kind of grind side by side. This would be most commonly associated with a transform boundary. And in some cases, if many different forces are pushing and pulling and grinding all at the same time, we can get a torsion force, and that occurs when forces twist. So materials can behave one of two ways when they have stress applied. They can either kind of survive the stress or they break. In elastic deformation, the material will return to its original shape after the stress is applied. Elastic materials will take a licking and keep on ticking. They will bounce back. So if you think about a rubber band in its normal shape, it's round, you can take that rubber band and stretch it into any shape you want, and as long as you hold that stress there, the rubber band will stay that way. But once you take your fingers out of the rubber band, it goes back to its original shape. So elastic types of materials, for example, asphalt is a little bit more elastic than concrete is. Wood is a little bit more elastic than steel is. Some materials just can't take the stress and they will break. Plastic deformation is when the material does not return to its original shape after the stress is applied. So for example, the lump of clay, I can apply stress to it and form it into a goofy head shape there, but once I take my hands away from the clay doesn't all of a sudden ooze down back into its original form. It will stay in that face shape. So plastic types of materials that won't return to its original shape, again, like concrete is more plastic than asphalt is, and steel is more plastic than wood is. So elastic materials can take the stress, plastic materials cannot. In general, when we want to build our buildings and bridges and roads in areas that can be susceptible to a lot of seismic vibrations, you're going to want to try to find as many elastic types of materials to build with as possible. Let's take a look here at the anatomy of an earthquake, if you will. The crack that the movement is taking place is what we call a fault. For example, the San Andreas Fault out in California is the main transform boundary. But what happens there is as the North American plate moves in a southeasterly direction, the Pacific plate is moving in a northwesterly direction. And eventually those plates are going to snag and catch on each other, and there will be a sudden release of energy from that fault. And we call that energy elastic rebound. The earth itself, the crust itself, we consider elastic because after all of the seismic vibrations that the lithospheric plates can undergo, they still return back to their original shape. So if you were, for example, to build a fence over a fault line, not a smart idea, by the way, we have seismic vibrations occurring, so we have deformation taking place. There's a big rupture of energy, and the plates now move, and the rocks will rebound back to their original shape. But the fence, however, the fence would be, in this case, considered plastic because it broke apart and it's not its original shape anymore. Earthquakes do not start on the surface of the planet, even though that's where we feel it first. Earthquakes start below the surface at the focus, or the origin of the earthquake. From the focus, the energy travels out in all directions, much like chucking a rock in a still pond. All of the waves come out in circular concentric circles from that rock. Same idea with the seismic shaking. From the focus, we start to get those energy waves out, and the first place that we feel it on the surface is what we call the epicenter of the earthquake. So the epicenter is directly above the focus, but it's on the surface of the earth. Different types of seismic waves will occur during an earthquake. We have two different types. One type is called a body wave, and we call this because it travels through the body of the earth. P waves are called P waves for a couple of reasons. Primary, P for primary. Also, if you can remember the type of motion that it has, primary waves have a push-pull motion. So we've got compression and tension happening all the time. Primary waves are the first waves to arrive at the epicenter. And primary waves have enough energy to travel through all types of matter, whether it be solid, liquid, or gas. So if you envision primary waves like a slinky, and if you constantly push and pull the slinky, some of the rings will be together and compressed, and some of the rings will be separated. That's much like how these primary waves travel through the body of the earth. The next waves to arrive at the scene are secondary or S waves. They also have a shear force, and their motion is up and down. Secondary waves are the second to arrive, and secondary waves only have enough energy to travel through solid materials. Once they hit liquid, or in the cases of underneath the surface, a natural gas pocket, they will stop. The surface waves that are the most noticeable to us and are really the ones that kind of cause the majority of the damage. L waves, or longitudinal waves, have a side-to-side motion. L waves are the last to arrive for the surface waves. If things are very, very bad and you are very close to the epicenter, you may experience what we call R waves or Rayleigh waves. These have both an up and down and rolling motion, much like an ocean wave that kind of comes up and crests over and continues that motion. So body waves go through the earth, surface waves travel along the surface. To measure earthquakes, we have a couple of different scales that we can use. The Mercalli scale is used to measure the intensity of the earthquake and the resulting damage. The Mercalli scale is not usually reported on late-breaking news reports of earthquakes because it's a little more subjective. Eyewitness reports are used as well as kind of assessing the post-quake reports of all of the damage. It's measured on a scale of 1 to 12, 1 being fairly minimal, 12 being fairly disastrous. Mercalli scales can be subjective because it would have to do, for example, if an earthquake happened in a very populated area. The Mercalli number would more than likely be fairly high because there's a lot of stuff in a populated area. There's lots of buildings, bridges, railroads, etc. So just taking a look here at some general levels. 1 is rarely felt by people. A 3 on the Mercalli scale, felt indoors by several. It would be like the vibration of a passing truck outside. 7, you would find it difficult to stand. You would notice it if you were in a car. Furniture and chimneys may be broken. Well-built buildings would be hardly damaged, but poor structures would have considerable damage. Once you get to 10, you have most masonry, which is brick, and frame structures are destroyed. You've got damages to dams and embankments. Water at this point can actually splash out of rivers, canals, and lakes, and it can actually bend railroad ties. If you're at a 12, the damage is nearly total. You can physically see waves on the ground surface. Lines of sight and level are distorted, and objects can literally be thrown into the air. A 12 on a Mercalli would be a very bad thing. The scale that you're probably a little more used to and that is more reported is the Richter scale. This measures the energy that's released during the earthquake. The strongest P wave that comes through an area is what we use for the Richter reading. The Richter's measured on a scale of 1 to 9, only because the rocks of the earth itself and anything that we build man-made can only take so much shaking before they'll break. There would be no 12 or 15 on the Richter scale because at about a 9 with that much energy, things will break. So to, again, measure the Richter, you use the amplitude or the height of the largest earthquake wave through the area. Some Richter readings here, and you can see also the estimated occurrence per year. The reason why we don't have those late breaking news reports is because many earthquakes are recorded but not generally felt by anyone. At under a 2, around a 5 to a 5.9, it's fairly damaging. We get about 800 of those a year. And the biggies, the 7s and above, we get a few of those occurrences per year. And the Richter scale is logarithmic, so a very small change in a decimal point number means a very large change in energy. This has been Physical Science 2, Chapter 12, Part 2 on Earth's internal processes.